Alright, hello, and welcome to another presentation. So, this one is about sequential and binary searches. Two very basic search algorithms that you will be expected to know in your AP Computer Science A class. So, let's go ahead and just move on in. Alright, so let's talk about why we even have these things, the need of it. So let's say we just had this array, the array being denoted by the curly Q brackets. Looking at this array, we're going to go ahead and ask a few questions about it. For instance, is there a 12 in that array? Is there a 1? How about a 7? Or is there a 6? Or how about a 168? Now, these are actually pretty easy to answer. You probably figured them out, quickly. Is there a 12? No. Is there a 1? Yes. Is there a 7? No. 6? Yes, and no for 168. There's our 6, there's our 1. Now we got them. Yeah, so that's pretty easy. Now let's take a little bit of a larger array. So now, in this array, let's get those same 5 questions in there. Is there a 12? You could answer probably, but since I'm kind of mean, I probably took all the 12s out of there just to mess with you and make you actually look. But really, take a look at that array. That's not an array that you want to search through. So this is where we want to bring in some kind of algorithm, some kind of way for the computer to handle it. Because oh, and yeah, by the way, there is a 12, there is no 1, there is a 7, 6, and 168. The 1 is the only one that is not in there. Anyway, so to take an array like this and search through it to find these things is really, really hard. So instead, I solved these using a sequential search. Now, the sequential search is a really basic search algorithm, which I'm going to show you with this unsorted list here. Up here, I have the indices where I'm marking I, and down here where we have all these other numbers are elements where I'm marking E. So the search is just basically moving from left to right, looking for the number we want to find. Now, if you're in my class, I would go ahead and ask you the question on the next slide, but instead I'm just going to go and explain to you what this word down here means, what this phrase down here means. So thinking about sequential search, I'm telling you it's basically brute forcing. Brute force is a solution to take the most obvious and least likely, least efficient approach. It's basically just searching through an array until you find your answer. So let's go back to our example over there. Let's say the number we were looking for was 3. All right, now going through it, what it would do is our program would look at the first number, ask, is it 3? It answer no, so it asked about the second number, and then the third, and then the fourth, and it found it, so it says, yes, we found it, which is shown here in our code by when we set our flag equal to true. Now notice, my query is a little different here. It's 33, and there's apparently 50 elements in this array instead of just whatever number was on the other side. So obviously, it's a little different of a situation. So that's sequential search, otherwise known as linear search. You have a query, you have, in this case, we have a flag to just figure out if you found it or not, and we're going to go through the array or array list, as is the case here, until we find that query. Very straightforward. It's not very efficient. Now, for an unsorted list, it is probably, I can't really tell you a better way of doing it, but let's think about binary. Let's move a little on. So this array is 304 elements in size, meaning that for a human it would take a long time to search through, but for a computer it would be very short. 304 is not a big number. However, what if that number were 304,000? As in this times 1,000. So that means like a whole lot more numbers to search through. Now that's going to take really long for sequential search. But what if it were sorted? Now, binary search takes advantage of the fact that a list is sorted. For instance, I have a much smaller list here of sorted numbers from 4 to 455. And we're going to go and do a binary search on it. Again, I have the code for binary search right down here. Here are the variables we need. Here is the actual algorithm for performing it. And, well, let's go and go through it. So we know the indices. I'm going to write the indices up here, just above our numbers. So binary search takes advantage of the fact that an array or list is sorted and cuts down the runtime of the program logarithmically. In computer science, which you will see if you go into CS in college, we test the efficiency of programs using a variety of systems. One of the more popular systems is looking at big O notation. So big O is where we have, we say the order of the algorithm is some variable expression. So for instance, sequential is considered to be order n, where n is equal to the size of the array, because the longest amount of time a sequential search can take is it goes all the way from the beginning of the array to the end of the array, meaning it does a number of steps equal to the size of the array or list. For binary, though, it's logarithmic. It's a logarithmic algorithm, meaning that for a binary search, we would say it's a big O of log of n, where n is the size of the array or list. Now, this is not something you really need to know for this class, but it's if you can grasp it, there's no reason why you shouldn't go ahead and grasp it and pick it up. It's a very useful thing to have, being able to figure out the efficiency of an algorithm. Obviously, the log of n is smaller than n. So basically our point is that binary search takes less time. And let's go ahead and just see why that is. Alright, so let's actually do this thing. So our query based on this code is 37. And our flag is still false. We haven't found that number yet. So we're just going to go and leave it like that. Alright, high is equal to the size of the list minus 1. Well, the list itself is 13 elements in size. Now we can count them. 1, 2, 3, 4, 13. Now, size minus 1, hopefully you can figure out, would be 13 minus 1, which is equal to 12. Low is just set equal to 0, and medium isn't set equal to anything right now. So what we're going to do is, so long as this low and this high have not crossed each other, we're going to keep looking at the element between high and low. So in this case, probably be around here. And we're going to see if that's our query. So let's go ahead and do an example. I'm going to do one little loop of this, one iteration of our loop, and then we'll talk about it again. So let's set median equal to high minus low divided by 2 plus low. So that's high minus low divided by 2 plus low. In other words, it's 6. Because, yeah. So median is equal to 6. That's where we're going to start off. Medium is 6. So let's take that now. We're looking at this number. Now our query was 37, right? We have it right over here. 300, we would say, is greater than 37. That's 37. That's what that number is right there. So we would say that list.get at medium is greater than query. I mean, we're looking here. So in that case, we said high equal to medium minus 1. So I'm going to go ahead and do that. Right now, I is equal to 12, but we're going to get rid of that. We're going to say it's equal to medium minus 1. So that's 6 minus 1, which equals 5. Alright, so now we have this new kind of thing set up. I'm going to say we get down here. So our flag is not true. It's not there yet. So we're not going to worry about that. So we're going to go back up to the top, and if low is less than or equal to high, which it is, 0 is less than or equal to 5, we're going to go ahead and change our medium again. So now, medium is going to equal 5, high, oh, yeah, actually, sorry, I said I would explain that now. So right there, what we found out is that this was not our number. We know it was not our number because it was too big. So therefore, we know that since this list is sorted, and that number at medium was too big to be our query, we don't need any of these other numbers. Right? And you can look at it yourself and see none of those numbers are our number. So knowing that none of those numbers are our number, we know that we don't have to check them anymore. Already, the amount of checks that we have to perform is cut in half. This whole side here doesn't matter anymore. We get to check half as much as we would have. Now that's going to continue going. Let's go ahead and get back to this point in the program where's my mouse? There it is. Alright, where medium equals high minus low divided by 2 plus low. So that's 5 minus 0 divided by 2, which is 2 since it's integer division. I'm going to go and erase this to clean it up. Alright, so plus low, which is plus 0, so it's fine. Okay, so 0, 5, and 2. So that means that we look at 2, which is medium, which is this one right here. No longer here, we're over here now. And we look at it and we see, oh, okay, 136 is, well, just like the other one, 136 is greater than our query, which is 37. So if that's the case, just like last time, I is going to be set equal to medium minus 1, which is 1, because it's 2 minus 1, which is 1. So again, we know that's not a number, and we know none of these are either. Again, we just ignored half of what we had left. So the end result is, notice how we've avoided checking 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. 9 out of our total 13 elements. That's pretty good so far. We're going to go one more time. So now medium equals high minus low divided by 2. Or 1 minus 0 divided by 2, which equals 0 in integer division. So now we take a look at the 0th element. And what we find is it's too small. 4 is less than 37. So that means we do this one. we're going to go and move medium up by 1. Or low equals medium plus 1. Medium's right now equal to 0, so low equals 1 plus 1. So now we go ahead and check it again. We're going to check it at element 1, because here, I'm going to clear some of this. Alright, so that was 1, that was 1. And this one now is going to be determined based on... Okay, there we go. Okay. It's going to be determined based on high minus low again, because low is still less than or equal to high. So here we are. 1 minus 1 over 2. Wait a minute. No, low is 0. No, wait. Low is 1. Dang it. Yeah. So this only goes while low is less than high. Then we'd be good. Actually, no, this could be less than or equal to. Sorry, I messed up there. Yeah, that's fine. High is 1, low is 1. Medium is equal to 1 minus 1 over 2 plus 1, which equals 0 plus 1, which is 1. So we look at the element at 1. We find 105 is greater than our query. So we do this one. So high equals medium minus 1. Medium is equal to 1, so it's 1 minus 1, which equals 0. We go back up to the top here. We see that low is no longer less than or equal to high. It's actually greater than now. Hopefully you can see that. How 1 is greater than 0. So we exit the loop. Our flag is still false. So we know that we did not find it. So we know that after having checked these 4 numbers, we checked only those 4 numbers right there, and we found that 37 was not in there. Notice, that leaves a majority of the numbers that we did not check at all, meaning that we got to find our answer way more quickly than we would have with sequential search. This algorithm here only takes a long time for a human to do. Computers can do it much more quickly than we can, and have less trouble with that. So even though it's more complex, it's actually a much more efficient way of doing it. So binary search works on sorted lists, taking advantage of the fact that they are sorted, allowing them to skip most of the elements that don't need to be checked. We could do a similar example where we actually could, find it. For instance, if we were to put query in for 266. In fact, I encourage you to go ahead and try that. Go ahead and try it for query equals 266. Alright, well otherwise I think that's all I have for you now. Hopefully you remember that linear search, here's that code for it. And binary search, here's the code for that one. Okay, I think that's it. See you next time.